should share the screen. And here we go. Today, our topic is clustering. Just to recap, in the last lecture, which was on a Monday lecture session, we covered two things. We covered k-means clustering and we covered hierarchical clustering. So before we continue into the lab, just a few things to summarize. First is clustering is different from supervised learning algorithms. It is not predictive modeling. It is something different. What is different about clustering? Would one of you like to volunteer? How is clustering different from classification or regression?
So that,
Go ahead.
Don't supervised.
What does that word mean? Like, in what sense is it different? Like, without the words, in simple words, like without using terminology, in simple words, what is different about clustering compared to classification or regression?
Asif, is it like a grouping of data points? Like you have different instances of the data points. You're trying to group it.
Yes, that is one way of putting it. Yes, that is correct. It's also the correct answer. Yes.
no prior training data set or like instructing the data, like how to figure out this data set. It just
That,
Supervised learning.
that too is part of the. Yes, go ahead.
Is it pattern recognition versus modeling?
Yes, very good. That too is part of the correct answer. So
Yeah.
all
So when you group it, like I think the idea is like so similar properties or features will be in a similar cluster. If the properties of those data points are different, most probably it will be in a different cluster.
We're not interested in predicting, right? So basically, that's the point.
So all of you have essentially touched on the answer in the right way. Let me summarize it. In predictive analytics, there is always an input space and an output space, right? A target space. The input space is the feature space, the feature vectors. And then you're based on the feature vector for each value of the feature vector, you're predicting a target value, either a real number, a measure, let's say how much ice cream you would the boy would sell on the beach, or whether it's a cat or a dog, or it's a cow or a duck, right? Identify the type, the categorical type. So it is a mapping from an input space to an output space. To learn that mapping or that function, this is a predictive model. You predict what the target value will be. Now, to do that, you need to start with training data from which the algorithm learns. That is the inherent nature of predictive modeling or supervised learning. Those words are essentially synonymous. On the other hand, in so called unsupervised learning or pattern recognition, what you have is no output space. You just have the data space. You don't distinguish between input and output space. All the columns of your data, if you were to think of it as a data frame, they all are part of the feature space. Right? So, given the feature space, the question that you ask in a pattern recognition is there a pattern in the data? One of the simplest patterns that you can find in the data is that data may be clustered, they may be near each other data points based on some measures of similarity. For example, if you look at lots of elephants and lots of ducks, in the feature space of size and weight, all the ducks will be clustered around one region, and all the elephants will be clustered around another region. But suppose you didn't know that there were different elephants. You're not thinking classification. Even if you don't, you would still, in the data space, find two different clusters of data. Right? So those clusters, they are points that are similar because of some reason. You don't know the reason. Like, for example, in the case of a cow or a duck and elephant, it's very clear they're two different animals. But when you don't know, when you don't have the target variable itself, All you know is that there is something that makes data points sort of flock together or group together in different groups, uh, and that is clustering. You find those clusters. The underlying belief is that between the clustering may or may not be because those points are inherently different. Sometimes just by the nature of the physical dynamics, they're different. For example, the stars form galaxies. The two galaxies may not necessarily be different in terms of their astrophysical attributes. They just happen to be two different galaxies. They may share a lot of things in common. You don't think of them as cows and or ducks and elephants, inherently different things. They just are different. They just happen to be not different. They just happen to be in different groups because of the dynamics of formation, right? When you see, likewise, if you see the beach and you see children have created piles or clusters of sand, those sand hills are not necessarily different, but they just are clustered. And so that is a subtle shift. When data is clustered or grouped because in the feature space, there may or may not be a difference between the clusters. Sometimes there is. And when you have a difference between the clusters, it actually gives you a lot of insight. For example, today, one of the most interesting areas of research is, can you use unsupervised learning, in particular clustering, to do classification, for example, or regression, classification in particular? So, for example, if you can tell that this cluster is made up of people, let's say you're looking at some biomedical markers, and, and you find one cluster of people, and you happen to notice that these people all have diabetes, and another cluster of people, and they don't have diabetes. You might have stumbled upon a way of classifying by clustering. So that is a happy accident or happy circumstance. You look for that. And so you have used clustering to actually do classification. But it is not necessarily so. Clustering may be done for its own sake. You may just be clustering data. Okay. So that is what we'll do. The other form of pattern recognition is what we'll do next time. It's called dimensionality reduction. Sometimes you find that in the feature space, most of the data is sticking to lower dimensional surface. So in a three-dimensional world, most of the data may be sticking to a plane, for example. And when you do that, when you find the plane near which most of the data is sticking, you say that you have, because a plane is two-dimensional in a three-dimensional space, you say that you have reduced the dimensionality of the data. For all practical purposes, you can think of data as belonging to some point in the plane, and you can put a coordinate system on the plane and say, well, I can give, instead of giving XYZ, I can create a new coordinate system with respect to the plane and just give it with respect to XY on the plane. That is dimensionality reduction. We'll do dimensionality reduction next time, but today is the lab of clustering. So usually when you do clustering and when you do it in your books, most of the problems that you are given, and quite often the problems that you get in real life, are very simple problems. And so these algorithms, the k-means clustering and algorithmic agglomerative hierarchical clustering, they tend to work very well. So it gives you the warm and fuzzy feeling that these are very good algorithms, and that's all you need to learn. Unfortunately, I would say that most of the standard machine learning textbooks, they give you the fallacious belief that this is all you need to know, k-means and agglomerative. And there are some esoteric clustering algorithms, but you can get away with these two. In fact, these are the only two they cover. Actually, I don't want to do that. So instead of taking simple examples, I've deliberately created an example which illustrates the entire complexity of the problem of finding clusters. And we will deal with this particular data set. So I've created this data set, and you'll see it. And you will see how different algorithms deal with this data set. And what I want to focus on is where it succeeds and where it fails. Are we together?
Asad, is this notes shared? Like I was not able to find this clustering algorithm.
Yes. I'm going to share it, add it to the tabular data right after class.
Okay.
I thought I'll walk you guys through it and right after. Actually, I should have done it in the morning, but I had a busy morning today. I was helping my daughters and so forth, so with their studies.
If you can't download this document from the tabular data, is that?
Yeah, you can't, but you will get your book, a physical book, right?
Okay.
Which will be much better. The reason I'm preventing it is because I'm updating this document every day. So whatever you download is obsolete. Right?
Okay,
You
no
may
problem.
feel that you have the latest doc, but it isn't the latest doc because I've just updated it and so forth. So wait a bit, you'll have a full physical, colored bound, hard bound physical book, which will be much more fun than just having a PDF around you. So just bear with me for a couple of weeks and then you'll have access to this. Huh? So, all right, guys. So, are you able to read it online though? Like in your laptop, are you able to read the notes properly? I hope you guys are able to. Anil, you're able to read the notes online, isn't it?
Yes, sir.
Okay, good. Yeah. So, all right. So, what I have done is taken a data set, which I created myself. It's called the Smiley data set. It's there on the GitHub, the class GitHub. Go to the GitHub and you'll find it there, ML100. Now, one thing for clustering, for me, whenever I think of clustering, I suppose because I come from a I have a very strong fondness for astrophysics. To me, clustering always evokes the images of galaxies. So I put this picture of galaxies there. You can see, naturally, you see nature forming clusters and so forth. So we'll do that. So here we are. We are taking this Smiley data set. What do we do with any data set? The exploratory data analysis. We load the data. So it's a two-dimensional data. Just two division. Now, I have given you a target t variable, which you should ignore, which actually tells you that if you did the right clustering, then there are actually there are actually 8 clusters, and data should belong. Each of which point should belong to which cluster. So I've given an answer here. We will see how well our clustering algorithms that we learned is able to deal with it. So, we load the data. I'll give you the solution today in both R and Python. I will walk through both. So R is simpler, quicker. So let me go through R. Loading the data is easy. Summarizing the data is easy. Plotting the data is again easy. So this is the plot of the data. I've colored it by the actual cluster identity of each point. And when you look at the data, what do you see? You see a smiley face, isn't it? Now, this data looks deceptively simple. It's actually not simple. It is hard enough that it brings most of the standard clustering algorithms to its knees. And I'll explain to you why it is so. Do you notice that the eyes are roundish? Right? So they are what you would call globular. But nothing else seems globular. The eyebrows, would you call the eyebrows globular? No, they have concavity to them, isn't it? Likewise, the smile has concavity to it. That this is triangular, not exactly globular, it's triangular. And then there are outlier points. Do you see this salmon colored points? The t is equal to 0, this colored points. They are the outliers. They don't belong to any cluster. So spend a couple of minutes thinking about this data and you will realize that actually from a clustering perspective, you get a clue that this could be a pretty tough data set to deal with. Fortunately, in real life, 80% of the time you won't get complex data set. 20% of the time you will get complex data set. And so your basic algorithms won't work. So so in other words, if you just know what we learned in the last lecture, it can work quite a few of the times, but often it doesn't work. So the clustering algorithm, what did I tell you? In K means you don't know K. So you have to try out different values of K and see where do you get that. What was the measure of goodness of a cluster, guys? Do you remember from the notes? Within cluster, some square distance. Do you remember that?
WSS.
WSS, exactly. So what this code does is it computes, it does the clustering for each of the values of k from 2 to max, it go up to 15 clusters. And the clustering itself is just one line. K means give the feature, tell how many clusters you want to see. Now n start is do it again and again and again just to find the best two, three cluster or four cluster, whatever. It is a good idea because sometimes the k-means clustering can come up with crazy answers. So you should never trust, do it once. You should do it again and again and take the best one. It's just a technical detail. So you have this clustering, and then what you do is you compute the WSS and you record it. And once you record it, you make a plot of it. The rest of it, this part is just the plotting. The main code is just line 8, which is doing the clustering. So if you know how many clusters to find, 5 for example, you can do it with just one line, namely k means feature and 5. That's what make R so powerful and simple. You can achieve a lot in one line. In this 24 lines, we have everything. We try every possible value of k. We also do the plotting of it. We and so forth. So when you do, and I would suggest guys that do the lab and understand this code. Let me walk through this. I'm creating an empty data frame in which I'll store k for any given k. What is the best WSS I got? Then I write a for loop. For each value of k, I go and do the k-means clustering, find the WSS for that value of k, and store it in the table. Once I've stored it, I do the plotting. I just plot it out. This is just the plotting code, right? So let's see what comes out.
A quick question. Is there a rule to set the maximum K in the...
No, there wasn't actually. This is one of the things. You have to look for the elbow, right? Once you have the elbow, there is not much point in going too deep after that. But where you'll see the elbow is a guess. So in the beginning, you start with 10, 15, 20, and then see if you didn't find an elbow, keep going. All right.
Asif, what is string as factors? F, right?
Which factor? String as factors. Oh, okay. Mm, uh, when you find like if you get string as factors is just the value. Like when you store k in this, k is numerical, WSS is double. When you create a data frame, if you get any string as value, right? Should you treat it as a number or should you treat it as a fact, categorical? In our case, we want to treat it as a number because both of these are numbers, numericals. Yeah. So even in the data frame, we write it as a number. We don't want it to be treated as a string by any chance. So string, actually, this part is unnecessary. You don't need to put it because
More as a cast as factor or cast as integer, right?
yeah, it is saying don't cast it as a factor. Yeah, leave it as integers,
Okay. Yeah.
which is what we want, right? Because these are numbers. So once you do that, let us see what comes out. Zoom out. There we go. Let's see. So we get this curve. You see this WSS versus K. When you look at this, guys, do you see any elbow here? Where do you see the elbow?
One between 2 and 4, or the one between 4 and 6. So I think 2 and 4.
Like so, yeah.
It's not
Okay.
very clear.
Anybody else would like to make a guess? Some other opinions, guys. Where is the elbow? Which value would you put your elbow at?
4 and 6.
Between 4 and 6. The 5, maybe 5, huh? Or
Like,
something like that. Maybe
yeah.
5. Maybe 3, as uh, Haripriya said. Yeah. So you can choose, but is the elbow very clearly visible?
No, no.
No, not clearly visible. So this is a clear sign that either the k-means clustering is not doing a good job or the data is truly not clustered. Well, in this case, we already visualize the data and we know there are clusters. So this is a clear hint that a k-means clustering is probably not doing a good job. So let us look at this diagram here. I've shown the clustering for each of them, and here Let me make it, wait, wait, uh, let me make it one page at a time, zoom out, continue single page. Uh, let's look at this. So you look at k is equal to 2. How many clusters do you see? And what I have done is I put a convex hull, or I've shrink wrapped the clusters. Does this clustering look okay? Half the nose belongs to the top cluster, bottom half of the nose belongs to the lower cluster. Would you consider this a good clustering, guys?
No. No.
Would you consider it a good clustering? Now look at k is equal to 3. Here it breaks it up into 3 places. Now you notice that Haripriya, you said that k is equal to 3 look like a maybe an elbow point.
Yes.
It is a reasonably clear clustering, except that it misses the fact that nose and lips should be separate and eyebrow and eye should be separate. But at least it did somewhat of a clean separation,
Yes.
right? But still not perfect. You go to k is equal to 4, and now things begin to get really bad. The nose and half the lip go to one cluster, the other half of the lips goes to another cluster. That doesn't sound good at all. Now, k is equal to 5 was something, I think it was Srinivas, you were saying, looked like a good cluster. And it's sort of here, at least the nose is a cluster in itself, eyebrow and eyes are a cluster, but the lips have become two different clusters. Right? And so, what do you notice? That in each of the clustering, there are imperfections. And you can keep going down. If you go to k is equal to 6, it begins to get worse. The lips have 3 parts. If you go to k is equal to 7, something interesting happens. The eyebrow begins to separate from the eye. Do you notice that yellow and this left eyebrow is separated, but the right eyebrow is still the same. By the time you go to k is equal to 8, lovely thing happens. Eyes and eyebrows are different clusters, as they should be. Nose is a different cluster, but it completely fails on the lips. The lips get broken up into 3 clusters, whereas we know that the lip should be one cluster, isn't it? And if you go to higher values of k, you realize that it doesn't get any better. Do you notice that? Sorry, it doesn't get any better. Would you agree, guys? It gets progressively worse after that. So k is equal to 3, k is equal to 5, and maybe k is equal to 8 are some possibilities. Let's look at this structure. And k is equal to 3 is this. Yeah, there is a good bend. K is equal to 5, a little bit of a bend elbow. K is equal to 8, not much of a bend. So at the end of it, guys, what do you conclude? Is it useful? You would say, maybe I could use k is equal to 3 or k is equal to 5. They're imperfect, but we could sort of use them at some level. Yeah. That's all you can say, but not terribly useful. Would you
So
agree?
isn't like the k-mean is to identify like a spherical blob?
Globular, yes, globular cluster.
Yeah. So
It is
because
one
it is the data set, like it does not have blob. Like
exactly.
if you look at the lip or the eyebrows, like it's not a spherical blob. It's a like a different kind of a blob. So maybe k-mean is not the right
Absolutely.
clustering
That's the
algorithm.
point I'm making. The textbooks tend not to mention this fact or emphasize this fact that k-means works only when you have globular clusters. It actually doesn't work otherwise. But in real life situations, uh, you don't always get globular clusters.
Oh, okay.
So the weakness of k-means, and I use this data to show the weakness of k-means clustering. It doesn't work well for non-globular situations. Right? So that is the point, which is why I feel that that the textbooks have they slightly misguide you. What about now? Let me use DBSCAN will do a bit later. Let's do hierarchical clustering. You remember hierarchical clustering? What do? You build those dendrograms. Well, there are so many points that this figure is very hard to see. But you can. What is the quality of a dendrogram? You can have as many clusters as you want. Right? You can have one cluster, you can have two clusters. By cutting here, you can have three clusters, four clusters, and so forth. When you do using a dendrogram, once again, this is the best you can do, which is 1, 2, 3, 4, 5, 6, 7, 8. K is equal to 8, very similar to k-means clustering. the 8, k is equal to 8 if you cut it out, right? This is what you get with the agglomerative clustering also. So the point is that, let me go back to a 2 view. Yeah. So when you do this, agglomerative clustering also doesn't help you. This is the code, by the way. Huh? Agglomerative clustering is just 3-4 lines of code. The code for all of these, good thing with machine learning is the actual coding part is very simple. Right? What are we doing in the first line? We are saying that the distance should be Euclidean distance, right? Which is a given. Unless you have a reason not to use Euclidean, you tend to use. Yeah. This is to, how do you know what clusters are good? A measure. One of the measures is called Ward hierarchical clustering measure. It is somewhat like WSS that you use to establish which clusters are good and so forth. And then all you do is you do the clustering, you use this method to find the clusters, and then you plot the clusters, and then you group the clusters. You can then find the groups by cutting the clusters at k is equal to 8. That's all it is. Huh? It's a very simple code to do that. And I'll now show you the Python code in a moment. But the lesson that you learn is neither k-means nor this hierarchical clustering are good. So what works? Let us, there is a different theory, and a very interesting theory that I'll tell you about, which is called density-based scanning. It basically says that clusters tend to be dense regions in the feature space, isn't it? This is a dense region. This is a dense region. So it takes a very physical argument. It says that imagine that each point had a mass, right? So places which have clusters in the feature space are places where the density will be high. Density of points will be high. So all we need to do is find regions that have high density and call them clusters. Very intuitive. It's surprising that this intuitive argument was discovered very late in the last century. I believe the year was 1998 when it was discovered. So when the first of these methods called DBSCAN came out, which is still very popular. When it came out, the paper, the guys who wrote that paper, they were immediately awarded the best paper of the year award in this field, right? Because this breakthrough was considered, this very simple idea was considered a major breakthrough in clustering algorithms. And in hindsight, it looks like such a simple idea, but then you implement it. Right? So the theoretical aspects, I'll talk about it next time. But how do you do? Well, the lines of codes are even simpler. 3 lines of code, 3-4 lines of code. One line of code does the clustering. And what this feature mean, epsilon and minimum number of points mean, I'll explain to you later. Just assume that we are doing based on regions that are dense. You find the clusters, you plot the clusters. That's it. And then you say, okay, let's see. These are some things like local outlier factor. What do they mean? I'll talk about that later. Local outlier factor is something far off and so forth. Is it etc. So we'll talk about that later. These are theoretical points. Just focus on the first 2 lines, clustering and plotting. Line number 2 and line number 4. Because the rest of it will make sense when we do the theory. And so when you do the clustering, this is what it says the clusters are. Would you think this is good clustering? It has defined these points, outlier points, it has left white in color because it is saying they don't belong to any cluster. And all the points that belong to cluster, it has colored as different points. So what do you think of this clustering, guys? Would you think that this is a good clustering?
Yes.
Yeah.
It certainly seems to have hit the nail on the head. And one reason I brought this point up. So this is actually one reason why these days, I mean, usually in most situations where I suspect non-globular structures, my first go-to approach is to start with density-based clustering. These density-based clusterings are very, very powerful. One of the methods I'll teach you in the next session is called DENCLU. Lovely idea. It's a field theoretic idea, and it finds clustering. It is massively scalable. Google has one of the fastest implementations of DENCLU, and you can imagine that it is massively used at the industrial scale, right, for large scale clustering exercises. My general experience has been that I prefer DBSCAN, or no, density-based methods, DENCLU, DBSCAN, etc., any day to k-means clustering. I rarely find situations where the traditional methods, k-means and hierarchical clustering, they do better than density-based clustering. Very, very rarely, if ever. Right. So this body of work that led to density-based clustering is very interesting. That's the context of our next lecture. But these
Joseph, sorry to interrupt. Is the density DB scan better than k-means because it keeps the outliers away from the cluster? Is that the major reason?
that is one. The other thing is it handles non-globular clusters very well. Look at the eyebrow. Look at the lips. It dealt with it very nicely, isn't it?
Right. Yeah.
The main advantage, two main advantages. First is it will mark outliers as outliers, whereas both k-means and hierarchical will assign every point to some cluster. It is it is blind to outliers, right? And the second thing is both traditional methods tend to do very poorly when you are dealing with non-globular clusters. Right? DBSCAN, not DBSCAN. DBSCAN is one density-based method. All the density-based methods, they handle non-globular structures very well. Right?
So what if your
And
data is clustered within each other like a target? And can you
I'm
still
sorry.
do these? If your data is like a target, like there's a bullseye and then there's a periphery going around the main centroid,
Oh yes, yes, yes.
DB scan can still
Yes.
detect. Let's
And
say
you'll be surprised that that density-based works actually very well with that. Right? What you're saying is imagine a bullseye and then a circle of another cluster and an outer circle of yet another cluster and outer circle of yet another cluster and so forth, right?
yes, sir.
Actually, it turns out that for that situation, the k-means will be a uniform disaster. Hierarchical will be a uniform disaster. Deep density-based methods will succeed just out of the bat. But see, density-based methods are not. There are situations where even density-based methods fail. So the field of clustering is filled. It's like a enchanted land of very, very powerful algorithms. And no one algorithm is perfect, but each algorithm addresses or is able to handle some peculiarity in the data. My general feeling is I rarely see k-means works well when
Asif, for some reason, I've become the presenter.
Yeah.
I think Asif was the.
Yeah, but Asif must have dropped off or something, but you can change the role back to him as a presenter, host. Looks like it's a network issue on his side.
So Asif is not there. I'll ask a question. So in this clustering, you saw the eyebrows and the mouth and everything, right? So what does that actually mean? Correct. They're not associated with any feature sets. So how do you quantify these areas and why those points are there? Correct. That part is not clear to me.
One thing I feel is would be the distance aspect. So the points near one eyebrow are closer to, let's say, some centroid within that eyebrow cluster, and it is far away from the other eyebrows, one point in the other eyebrows cluster. So I think the distance aspect that we saw in the last lecture, I think that should be what I feel that should be the distinction between if one point comes in one cluster or comes in the another cluster.
Okay.
I don't think you can base it on centroid if it's density, because otherwise it would be globular.
Yeah, yeah, that is also true. I mean, but the underlying idea would still be distance, right? I don't know if for k-means, yes, you're right. If it's globular, so we tend to get a circular distance around something, find the radius. But yeah, it's interesting. What is it in k-mean?
So in the regular algorithms, at least you are quantifying by something, right? This is weight. That's why cow is cow and duck is duck, or beak or something. But here you are having clustering, but on what basis, right? So you split the points, but then somebody asks you what are there, why the points here and why are the points there, right? So then it's not clear how you kind of answer that question.
Yeah, so one thing I can share with my own experience about this is, so the company that I work for, we use DBSCAN there. And what my company does is we have a product, we have an application. So if you have that application installed on your phone, it will get you connected to any open hotspot all around the world. So it has like a global footprint. So it may be Google, Starbucks, or Panera Bread, or SFO Terminal 2 Wi-Fi. So how the clusters are formed is, let's say Terminal 2 has 10 clusters, and we use DBSCAN to do that. And then those 10 clusters would have, hypothetically 10 hotspots in it. So that would be 10 data points in each cluster. So you'll go ahead and rank each of those 10 hotspots, and then the next time you are in Terminal 2, it will get you connected to the best ranked hotspot in it. So that's how at least the clustering takes place. So for your question, it is somewhat related to classification as well, right? So one eyebrow is separated from the nose, let's say. So uh, uh, at least in my case, we do not do any classification. It is purely clustering. So there's a specific different set of hotspots in cluster number 1 in Terminal 2 and cluster number 2 in Terminal 2.
Okay, I think you answer that question. There is a feature set, or there is some sort of basis of the quality of the hotspot, correct? So that tells you which is the best.
Correct. Yeah.
Thank you.
Does anybody have Asif's number?
Yeah, I called him, but he's not there.
So Dennis, you take over till he comes.
Hello, guys. Can you hear me?
Yeah,
Oh, goodness. When did you guys lose me? I didn't realize. Um,
probably 10 minutes ago.
Yeah.
5 minutes ago. Oh, good. Let me rewind and say the things again. What was I talking about the last time? Was I going? Did I do the Python part of the code or not? Should I do it again?
You did not do it.
Okay. So we were starting with the DBSCAN, but I did the Python k-means clustering. Did I do that?
No, you did not.
So, but I finished the R part, isn't it?
As if we can't see your screen also now.
Oh goodness, this is pretty bad. I don't know. This is. Oh, and I can't even share it. Not available. Maybe port 9000 and TCP are blocked. Okay, I think WebEx is having a problem. Guys, stay here. I will just kill this meeting and I'll come back to it again. Huh? And I'll pause the recording just to be safe. Good. And where am I? Oh, here am I. Okay, means. So doing it in Python is no different from doing it in R. It just tends to be a little bit more verbose in the visualization part. The reason being for visualization, Python doesn't have one-liners like plot and so forth to just do it yet. People are trying to mature the libraries. Eventually it will be there, but as of this moment, you have to write a little bit more code to do the visualization. But the actual machine learning part, the clustering part, all of those are one-liners. In general, clustering is much easier than your supervised learning, your classifiers and regressors. In clustering, you will feel that it's a much simpler topic from a doing perspective. So here we go. We have data. You look at the ground truth, and then to do k-means clustering, again the same for loop. In this for loop, we go through different values of k and find out. Uh, the loop is exactly this, more or less the same. This finds the clusters, and this plots the clusters. Very almost identical to the C, the K, I mean, sorry, the R code. When you do that, the clusters that you find are nearly identical, I mean, exactly identical, in fact, to what you found in R. There's no reason why the same algorithm in two languages should produce different results. It's good. The scree plot, how do you plot the scree? This is it. The plot, the scree plot. We have that. And then once you have the scree plot, you realize that there are no clear elbows here. The best you could think of is at 3 or at 5. Yeah, and which bears out, just to remind you, that 3 and 5 looked fairly decent. 3 was this. The nose and the lips are one cluster. Each of the eyes are a different cluster. Eyes and eyebrows are a different cluster. K is equal to 5 was actually pretty neat. The eyes are a different cluster. Nose is a different cluster. But the lips get split in two. Right? So not quite perfect, but it's about as good as you can get. So this was for Python, and the same thing for density-based clustering. Density-based clustering in Python, again, given the ground truth, this is the same code repeated. This is nothing. So the actual code is just a couple of lines, but then comes the visualization part. Unlike R, where to visualize it is just one line of code, in Python, as of this moment, you have to write quite a few lines of code. It's a little bit messier. And so this is the bit of code for data visualization. So here I would like to say there's a tip I will give you guys. When you do machine learning with Python, in general, you'll find that scikit-learn is very efficient. It's very good. It's almost like R. A few more lines of code perhaps, but nearly as good as R. But the visualization part, the maturity is not yet there. So you have to write visualization code, right? Using matplotlib, you have to write a bit more code to visualize the data. And so become good with Python visualization. Become good with matplotlib and Seaborn and all of these libraries. Try to spend some time and becoming good at it. Now, you may say, well, that's not really machine learning, that's just data visualization. But the fact of life is, whenever you work, you will be expected to create this visualization. See, in mathematical disciplines, mathematical results are very hard to explain to businessmen. It is the visualizations that tell stories that makes it accessible to the common man. And so the beauty of mathematics often is conveyed through the visualizations we create around it. Gradually become good at the visualizations. Spend some time and become good at the visualizations. So all this code, I can talk about it one by one. What I'm saying is you're taking the points and you're setting it to 0. Then you're saying which cluster does each point belong to? Does it belong to this cluster? Estimated number of clusters is 6. And then what do you do with each of these clusters? By the way, this colors is a color scheme called spectral. There are many color schemes in both R and Python. Usually they come from the Color Brewer package, an excellent package that is sensitive to colorblind people. Yeah, and they have aesthetically pleasing color schemes. Just use them. Don't invent your own color scheme in general, unless you are really confident of your artistic ability. Most people use an existing color scheme. Right? So once you do that, then all you do is you plot those points here. You do that. So when you look at this, once again, it has succeeded in doing what we did with R. Just to give you a comparison of this code versus this much of code versus the R code, you can see where's the R code. Yeah, you can see that here we achieved it in 3 lines of code, right? 1, 2, 3, 4, maybe 3 lines of code here, and then the local outlier factors and so forth. Right? Visualize the result. 2 of them, good enough, right? Or 1 line to cluster, 1 line to plot, so much easier. But in R, in Python, you have to do more. Relatively speaking, you have to do a little bit more coding. You have to just get used to the coding, because if you look at the machine learning part, it is still 1 line. The rest of it is just visualization of the clusters. So quite often, obviously, you will have your own little libraries of code to do the clustering. Libraries are maturing. More and more people are coming up with good libraries. Or one library that I suggested to you, which is very good to simplify your, the visualization of machine learning models and clusterings, was the Yellow Brick library. So let me take a moment to take you guys to the Yellow Brick library. Which I have mentioned before, but might as well mention again. If you go to the Yellow Brick library, and by the way, I should have used it in the notebook. This notebook I created before the Yellow Brick library. So Yellow Brick, no, not yellowbrick.com, yellowbrick.org maybe? No, Yellow Brick, Yellow Brick library. Unleashed, Skikit Yellow Brick. Okay, here it is. This is the Skikit Yellow Brick. By the way, these links are there in the document that I have, right? If you go to in the end, you'll find all the important links. You'll see it there. So you can visualize as an API if you go to. So there's a clustering visualizer. And as you can see, it helps you show the silhouettes, like for example, see the clusters and so forth. And are there examples here? Let me see if there are examples that they've given. Your color scheme, frequently asked questions, quick start. Let's go to the quick start and see if they have examples. Yes, so you'll see a lot of examples here. But let's see the examples for clustering. They must have examples for clustering about the data. This is feature extraction and so forth. Mm, yes, clustering visualizers. Well, they don't seem to have examples that I can show, but I will post those examples. So here's here's the elbow method. It is showing you that, and then quick methods, API references to make the scree plot, and then Silhouette visualizer. But they don't give you a visualization here. It's pretty useful. It will do pretty much what I did with the code. Now that the yellow brick library is there, I would encourage you to use it, and I'll also post code based on that. This is intercluster distance map. How distant are the clusters from each other? So make yourself familiar with these libraries.
Also for the clustering, I think without visualization, it's hard to see what the algorithm that we did has done to the data. Is that correct? Or can we still read it
Oh,
from
yes,
this?
absolutely. Clustering, you have to visualize it. You have to take some samples of the data. Even if you have to project it down to 2 dimensions and then visualize it, you should always visualize the data, because how how else would you know that your clustering is good? Try your best to visualize it. If you simply cannot, like, let's say your data is at 200 dimensions, it's hard. But then you use techniques, like there are certain techniques I'll teach you next time, dimensionality reduction techniques. PCA is the simplest of them, kernel PCA. Then there is something called TSNE. Then there is UMAP. There's a whole family of techniques. In the next workshop, ML200, you'll do a large number of them. This time you'll just do PCA, the foundational one. They help you reduce the dimensionality of the data. And one advantage is you can then visualize the data in lower dimensions. Right? So so that is all I have, guys. Clustering from a doing perspective, lab perspective, is quite simple. Especially if you do it with R, it's very, very easy. Python is also very easy, but you just have a few more lines of code. That's all. Any questions, guys?
Asif,
Mhm.
so I see these eyebrows and eyeballs and the nose and stuff like that, right? So in this case, what are you quantifying these points to? Is it some X or Y? What are those values? That's the confusing part for me.
You mean what values? The X and Y, they're just the locations of the points.
Okay, so it's just one kind of dimension and just location of the points.
That's right, quite literally. So, for example, this could have been a picture. Imagine that a photo is there of a face, and I ask you to cluster the pixels. You quite literally, this is a very simplified picture of a photograph, and you're finding clusters in the photograph.
Okay. But if you had talked about previously, right? So you're giving data to this algorithm, and you do
Yes,
not know what are the different features of the data.
that's right.
Then it comes back with one feature set and plots it accordingly, correct? And so that then you know that okay, it could be location, could be something else, could be color.
Yes. No, certainly. You tell it what are the feature sets, then it goes about clustering. And then the question that comes is, are the clusters good or bad? Are we together? So I'll take another example. Suppose you have uh, a, a picture in which there are three flowers in the picture. Now, they have a certain color. Let's say that the color of the flowers are orange or yellow pictures, right? It's surrounded by green leaves. So if you were to cluster, each of the flowers will stand out as a cluster, isn't it? Potentially the leaves will stand out as a cluster. But let us say that there's a general background of greenness and the three flowers are there. Surely you should be able to detect the three flowers as three clusters. That's the thing.
Got it. Got it. Thank you. Thank you.
So I'll post a lot of practical examples of this clustering. Let's do a few real life allergies. All right, guys, that's all I have. And then I'll stop the recording if you guys don't have a question.
Hey, Asif, have you posted the written notes for last section?
Oh, last time's written notes I didn't post, right? Let me do that right away. I posted the video. I hope you have the video, but I didn't post the written notes. I'll do it right away.
Okay.
And I'll post this recording also right away. Let me stop the recording now.